Hello students, welcome to this lecture on data path subsystems, and we'll be looking mostly to the adder. In this first particular module of the adder circuit, we will look at the circuit level designing of the adder. So what we'll be doing is we'll look into the 1 bit half adder and then the full adder, and then go about understanding the layout of the 1 bit full adder circuit. And subsequently, we will also take a look into the adder subsystem. So if I want to make it into an 8-bit or a 16-bit or a 32-bit adder subsystems, how do we go about designing those in the future lectures? Right. So let's begin with this particular, the adder circuit, understanding the adder circuit. So as we know, the half adder, which doesn't involve the carry input, and then has only 1 bit of A and 1 bit of B, and then we want to get the sum, the summation of the 1 bit of A and 1 bit of B, and then the carry out due to the addition of the 1 bit of A and B. So in this, the two input bits where the carry input is not allowed considered, we will have 4 such combinations starting from 0, 0 to 1, 1, and then we will have 4 such output values. So for 0, 0, the sum is 0, the carry out is 0. For 0, 1, the sum is 1, carry out is 0. For 1, 0, the sum is 1, the carry out is 0. And then for 1, 1, the sum is 0, and then the carry out is 1. So in that sense, if I look into the sum bit, wherever it is 1, it is either A or B is either 1, and then the other one is 0. So we will have the XOR operation of A and B. The XOR operation of the input A with that of B will give us the sum bit. The carry out, if I consider, if I look into the logical values of 1, it is only 1 here in the last combination when A and B is 1. So the carry out for a half adder will be nothing but A and B. So hope this is pretty clear to everyone. So for a full bit, for a full adder, we will consider not only A and B but also the carry input. It may be the carry input coming from the previous the input additions. So if I consider this 3 inputs, I will have 8 such combinations. So this will be 8 such combinations. And then we will have 8 such output combinations of the summation output and then the carry output. Right. So if I look into, if I start looking into the input combinations from all 0, 0, zeros to all 1, 1, 1, so we'll get the sum and then the carry out. And it's very interesting to find out, for which particular input combination the sum is actually 1. So the sum is 1 here when the C input is a 1 and then the other two are zeros, and then the sum is 1 here when the B is 1 and the other two are 0. Sum is 1 here when it is A is 1, the other two are 0, and then 1 here when all the 3 inputs are 1, right? So for the inputs where it is for the inputs where it is 2 of them are 1s, the sum is actually 0, and then where it is 2 of them are 1s, it is 0, 2 of them are 1, it is 0, or all of them are being 0, it is 0. So in that sense, the sum is actually can be considered as an XOR operation of all the 3 inputs. So it will provide either, it will give us the odd number of 1s within these 3 input combinations. So that's why the sum is considered as an XOR operation of all the 3 inputs, which is A, B, and the carry input, the C input. Carry out is again very interesting to see. If I consider the carry out, let me take a different color. So if in this particular combination the carry out is 1 when we have B and C to be 1, the carry out is 1 here when A and C are both 1s. Carry out is 1 when we have A, B to be 1, and it is 1 finally for all the 3 combinations to be 1. Right. So for all these 3 combinations, we can easily say that with the majority of the 3 inputs, with the majority of the 3 input, that means if the majority of the 3, if at all it is 2 of them are showing 1 out of these 3 combinations, A, B, C input, if 2 of them are showing 1, then carry out is 1, right? If all the 3 are showing them 1, then definitely the carry out will be 1. So this is called as a majority gate with the inputs coming from A, B, and C input. Its a logical expression is nothing but AB plus BC in plus AC. Right, hope this is clear for the full 1-bit full adder. This is again a 1-bit full adder. So if I consider this particular portion, this is nothing but the previous 8 input combinations with the output values associated with it. Here the addition is nothing but the propagate and the generate bit. I think this is going to be very useful in designing the higher order at a subsystem level, the higher order the adder blocks. This propagate and generate bits, which are kind of evaluated from the input combinations, and that will be used for generating the higher order adder bits. So just to complete the truth table, I've added the propagate and generate bit. And so let's take a look at the propagate first and then take a look at the generate bit. So the propagate bit, it is 1 and 1 here. When when you consider the C input, the carry input is 1 here, which is propagated to the carry out, right? Or or if the 0 is there, it is propagated to the carry out, and it is 1 here, it is propagated to the carry out here. Similarly, C input is 1 here, it is propagated to the carry out, and if it is 0, it is propagated to the carry out. Right. For the other combinations, when the C input is 1, it is propagated as 0, so that will not be considered. So what I meant is, this 1 and 1 bit, the propagate is 1 only when we consider for an input combinations, when the C input is 1 and it is propagated to the carry output, right? Without generating the carry. Now, how do we define the generate? So the generate signal is without C input, right? If the inputs A and B, it is able to generate the carry. So that is possible only when A and B are 1, right? And if it is able to generate the carry here, right, then the generate signal is 1. Right, so out of all these 8 combinations, we can see that the carry out is actually 1 in 3 of the combinations, or rather in these 4 combinations, the 3 of the combinations, this one, and this one. This one and this one, in the 2 combinations, the carry input is 1 here, and that's how it is generating the 1 here in the carry out. And for here, when the carry input is 1, we are getting the C out to be 1 here. Only for these 2 conditions, the carry output is 1, and it is inherently generating a carry because of A and B, both of them are 1. So the generate bit, or whatever, the G is nothing but A dot B. Right? So inherently it generates a carry, that is when the generate bit is 1. The propagate bit is 1 when we say that the C input is propagated to C output without inherently generating the A and B is generating a carry. So that is possible only in this particular 2 combinations, right? When C input is 1 and C output is 1, it is propagated to 1, and then when C input is here is 1, it's propagated to the carry output as 1. The only because the A and B here, either of them is 1, right? That is when, and then C input is 1, then that is how the C output is propagated. Right, so for the propagate signal, it is these 2 combinations is 0. This is 0 because anyways C output is 0, and this is 0 because A and B is inherently generating a carry. So that's why we say that it is not propagating, and rather it is generating. And this is 1 and 1 because here the C input, which is generated in the previous lower bit, the generated carry is kind of propagated in this present bit. Right, because my A or B, one of them is 1, right? So that defines the generate and the propagate bit, which will be useful, which will use it to design the higher order adder systems. Right, so generate means without C input, A and B should be able to generate a carry, and then propagate means C in should be propagated to C output without generating a carry. Right. So hope that is clear. At a transistor level, how do we design this 1-bit full adder circuit? The sum bit is given by this particular expression of A B bar C in bar plus A bar B C in bar plus A bar B bar C in plus A B C in, and this is arrived from the truth table, whatever we had seen in the previous slide. right? So the adder circuit as such, and if I consider the sum and then the carry out, it is nothing but it's a mirror topology. Mirror topology in the sense, if I actually get whatever is there in the pull up side, the same thing can be done in the pull down side, or vice versa, right? So this particular expression can also be written as, within the CMOS technology. If I want to have a pull down circuit, so then I will get a complement of that. And so this A B bar C in, when it goes under a complement bar, under an inverted bar, so I'll actually get a inverted topology here. So that will be, instead of A B bar C in, it will become A bar C A bar B C in. It becomes kind of an inverted expression of this. And A bar B C in bar will become, so this particular expression will become A B bar C in. Right, and then A bar B bar C in will become A B C in bar, and A B C in will become A bar B bar C in. Right, so this particular sum is equal to the inverted expression of the individual expressions of the sum expressions that has been written here, right? And then it becomes a complement of that. Right, the advantage of complement is we can easily have this circuit, design the circuit in the pull down side, and then take the output as directly the complement of whatever we have given here. Right, so the sum is nothing but this particular expression which we have seen. And now how do I actually design this at a transistor level? So at the transistor level, we will take A and A bar, right? I will design this transistor as A and A bar. And then we will have B bar here, B here, B bar here. So I need 4 such transistors. So I'll have B and B here on the extreme sides, and then B bar with the input given to the 2 transistors. Right, so this, if I connect either A to here or A bar to here, it will be actually be A in series with that of B bar, or A bar in series that of B bar, right? And then finally, if I want C in and C in bar, so I will take the 2 transistors here with one of them as C in bar, the other one is C in. So I have now I can easily connect in series between this between this 1 2 3 4 5 6 7 8 transistors, and then get this 4 different expressions, which will give us this pull down output, right? So if I connect this A to that of B and then B to that of C in bar, so I'll get A B C in bar expression. So A B C in bar, A B C in bar is done. And if I connect A with that of this one B bar, and then this gets connected to C in, so I will get A B bar C in, A B bar C in. So this one we have arrived at the transistor level connection to get this particular expression. This too we will see with A bar. So A bar B C in, A bar B C in. So this particular connecting this 2 transistors and then this 2 transistors by this blue wire, I will get this particular expression A bar B C in. And then finally A bar B bar C in bar. So A bar B bar C in bar. So I've connected this particular blue wire and then this particular blue wire, completing this expression. Right. So having this completes our pull down design. Now the pull up side is nothing but a mirror topology. So I will have the same level of same transistors, C in bar C in, and B bar B, and then A and A bar on the pull up side, which will be connected to the ground rail instead of the which will be connected to the VDD rail instead of the ground rail. And then I will do the similar connections, and then the inputs will be similar, A bar B bar B, C in bar C in. I will do the similar connections on the pull up side, and then I'll achieve the same expressions. In fact, I'll get the same expression here. So the sum will be nothing but the complement bar, or rather the bar here, and then this particular 4 expressions, which will be the output. So the output here, if I complete the pull up side, I'll get the Y as nothing but the sum output. Right. Remember that generally in a conduction complement topology, what we will do is, if I have 2 of the transistors in series, in the conduction complement topology, in the pull up side, I will have the 2 of the transistors in parallel. Right. Whereas in a mirror topology here, it will be the same topology which goes into the onto the pull up side. Right, and then the reason is nothing but if I actually change this instead of a bar, I'll change it to A, or B bar to B to B bar, and C in to C in bar, I'll actually get the same expressions, right? And that's the reason why the mirror topology is kind of really useful for the adder as well as the adder circuit, especially to extract the sum and then the carry output bits. Right, so the carry output is given as A bar, B bar plus, if I consider the C bar to be outside, it will be A bar plus B bar. And then just to complete the sum output, we will have 1, 2, 3, 4, 5, 6, 7, and 8 transistors on the pull down side, and then 8 transistors on the pull up side, so it will be 16 transistors. And then going forward, the carry output here. So with this particular expressions, we will get A and B bar in series. So this completes this particular expression, A bar and B bar, and then C bar in series with that of A and B, which are in parallel. So A bar, B bar in parallel with that of in series with that of C bar. So that completes this particular expression. So I will have 5 transistors on the pull down side, and then I will have the similar topology. So I will have, to complete the C out, I will have the 5 transistors on the pull up side with a similar arrangement, and then we will get the C out expression, which will take around 10 transistors. Right, remember that this A bar and then this B bar and then this, and then in the previous sum expression, we had A bar, B bar, C bar. So I need to get, the complement of the inputs. So the complement of the inputs means inputs are A, B, C, and the complement of that will be A bar, B bar, and C bar. So I'll require an inverter circuit. So for each of them, I'll require 2 transistors. So for 3 inputs, I'll require 6 transistors. So the total number of transistors that will be required to extract the sum and then the output, carry output for 1-bit full adder design will be nothing but 10 transistors for the C out, and then 16 transistors for the sum, and then the 6 transistors for getting the complement of the inputs, right? So I will need to design 32 transistors, right? So 32 transistors turns out to be very large for a single 1-bit full adder. So if I want to actually do for a 32-bit adder system, it will be 32 transistors multiplied by 32, pretty large. Now, can we actually save some of the transistors? Can we make it a little bit more compact? One such design is this particular compact design. One is where we can actually generate the C out bar, and then C out bar is nothing but AB plus AC plus BC the whole bar, which will be I'm generating the C out bar. So to extract C out, I will have to have an inverter here from the C out bar. But nevertheless, if I can do the C out bar and then take an inverter and then get the C out, and if I can get some bar and then take the inverter and then get the sum, and having the number of transistor designs, if it drastically reduces, or whatever the number it reduces, if it is still less than 32, it is worth pursuing that. So C out bar will be nothing but AB plus AC plus BC, which will be AB, and then taking the C common, I'll get A plus B. So this particular AB plus C into A plus B, so all the inputs are not complementary inputs. So whatever is the input, A, B, and C, we have just used it to the transistor level. And remember that A, B here will be nothing but 2 transistors in series, and C transistor will be in parallel with that of A and B transistors, and then the output of that will be the C out bar. Right? This sum, the complement sum expression or the sum bar expression is written as the whole bar. And underneath that, it will be ABC plus A plus B plus C, or the ANDing with that of the C out bar, which is generated here, right? So this C out bar goes here, right? So this C out bar will goes to a transistor, and then this transistor on the pull down side, which will be in series with the 3 of the transistors in parallel, right? And then this will go in parallel with that of 3 of the transistors in series, and then we will get the sum bar output. Right. Once we get the C out bar and then the sum bar output, we will be able to connect to the inverter and then get the sum output and then the C out output. Right. So what I meant was, we will first generate the C out bar and I have written only the pull down circuit. The pull up side will be exactly the mirror topology. So it will be the similar transistors and then the mirror of that. which will come onto the pull up side. On the pull down side, we will, as we said, C transistors in parallel with A and B, and then here the A and B will be in series. Will get connected to the C out, and then this particular, this particular line will be C out bar. The C out bar will go to a transistor which will be in series with that of 3 of the ABC transistors in parallel, and this will go in parallel with that of A, B, and C, which will be in series. Right, so I'll be able to generate some bar, I'll be able to generate the C out bar, and if I now try to calculate the number of transistors, it will be 1 plus 2 plus 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, and then 12 transistors on the pull down side, and then 12 on the pull up side. We will get 24 transistors to get C out bar and sum bar. And then if I connect an inverter here to generate C out, and then connect an inverter here to generate the sum, I will have to spend 2 transistors here, 2 transistors here. So I'll have to add 4 more transistors, and finally within 28 transistors I get the C out and then the sum expression. Right, so the C out logical output and then the sum logical output we will be able to extract. Right, so with the 28 transistors. Now, just to complete the 1-bit full adder using a 28 transistors, I've just drawn the layout diagram here. So the stick diagram basically, and then the stick diagram, and then this I have completed both the PMOS side as well as the NMOS side. So that means that the N diffusion line here, and then the P diffusion line here. Right, so and then this is the VDD rail, and then this is the ground rail. So just to get back into the transistor level diagram, so first we will be generating the C out bar, and then going ahead and then generating the sum expression. So similarly in the layout also, we will start from the left side here and then go to the right side of the transistor design. Right, so looking at the left side, so this will be nothing but the C transistor. So the polysilicon of the C will go here, and then the diffusions of here, one will go to the C out, the other one will be going and connecting to the A and B transistors which are in parallel. So the other diffusions of A and B, so the other diffusions of A and B are connecting to the ground. Right, so if I want to do that in the stick diagram, so I'll have this A and B transistors, and especially if I've drawn for the pull down side, and I said that it will be a mirror topology, mirror replica image of on the pull up side. So let me have a look at the N diffusion, and then the P diffusion will be nothing but the similar thing, similar connections. The only thing is the connections will be to the VDD rail, and here it will be towards the ground rail. Right, so looking into the N diffusion lines here, if I have A and B polysilicon, right, on one side it gets connected to the ground, both A and B transistors. On the other side it gets connected to the C transistor. Right, so I will have the A transistor which gets connected to the C transistor here, so the C diffusion, and then anyways B is anyways having the merge diffusion with that of the C. So I have this connections and then this connections. Right, so that completes this particular portion. So then the next portion is A and B, which will be in series and then connected to the ground. So I will have the A and B polysilicon. Right, on one side it is connected to the C out, and then the other side it is the ground. Right, so this completes the C out on the pull down side, and the pull up side will be the mirror replica image of the same thing what we have done here, because the transistors will have the mirror replica image. So the only thing is, instead of ground, it will be connected to the VDD rail. Right, and then we will be left with this point and then this point. So we will need to have a kind of a metal connection here, metal line here, which will be connecting and then saying that this will be the C out line, right, or rather the C out bar line. Right, so this completes my C out bar line. The C out bar line actually goes to a transistor here, so that's why I have drawn this C out metal line which gets connected to the polysilicon of C out bar. Right, so let me go quickly and have a look at the transistor level. So this will be the transistor, the C out bar line, which is connected to the transistor or the gate of the transistor here, and then we will have A, B, and C in parallel on one side of the diffusion for all the 3 transistors. It is getting connected here, and on the other side it is actually the ground. Right, So if I look into the stick diagram here, I have A, B, and C. On one side, it is getting to the diffusions of the Cout bar transistor. So this is that transistor where C is anyways having a merge diffusion, and A and B's merge diffusion is getting connected to this the same the diffusion of the Cout transistor. Right. So all the three transistors are connected. On one side, it is connected to the Cout bar's diffusion. And all the three transistors will go and connect to the ground. So we will have the A transistor here, which gets connected to the ground, and the B and C, which is having a merged diffusion capacitor, merged diffusions, which will get connected to the ground. And similar mirror topology will come onto the pull-up side. We will have these two connected, or rather this two connected here, and then this will get connected to the VDD rail. Right. So this completes the ABC in parallel with that of the Cout transistor, which will be in series. The final one so is the ABC in series. So the C transistor will get on one side it is connecting to the B diffusion, and on the other side it is the ground. Right. The A transistor on the other side it is the sum bar output. So if I look into this ABC, I will have the C bar, the one of the diffusion, C bar is connected to the ground, and then similarly on the pull up side, it is connecting to the VDD. And ABC on B side, on the A side, the diffusion is getting connected to the sum bar. Right. So now we have this sum bar on both the pull up side and then the pull down side that needs to be connected by a metal line. Right. So this completes the layout or the stick diagram of the 1-bit full adder. And we can easily calculate or evaluate what is the area that it occupies. And this particular stick diagram on the layout form is also available in the very first page of your textbook which you are referring, which is the Western Harris textbook. Right. So so this gives you what kind of designs, digital subsystem design blocks we'll be referring to from here on.